I want to say about the fields we're going to be working with, and I wanted to make sure you don't get confused about this. You see, the rationals happen to sit inside the reals, which happen to sit inside the complex numbers. So Q is a subset of R is a subset of C. You could think of it like that. And quite often you could be in the reals and you might have a matrix that just happens to be composed of rational numbers, but you're still working in the reals. We could, well, I haven't introduced vector spaces and scalars. When we do that, we have to be very careful about the system we're working in. So we might have something in the rationals and we might multiply it by a real because we're working in the reals. But that's not the point I wanted to make. The point I want to make is that this is something different. So you might say, oh, well, the field of, say, two elements. Well, if we have zeros and one, well, 0 and 1 are in the rationals. But we can't get confused and start thinking like that because it is not the case. The multiplication here is different. So it's not a structure. I mean, set-wise as elements, yes. 1 and 0 are the elements in the field of two elements, and 1 and 0 are both rational numbers as well. They're rational because you can write any integer as a rational number by writing it over 1. But don't assume that this is a subset of this, because if we're multiplying here, we're doing something very different than if we're multiplying here. And I guess for a simple example, consider something like this matrix. 1, 1, 0. Let's put zeros on the off diagonal here. Okay. So if we're in the rational numbers, what would the determinant be? So I want to know what the determinant of this matrix is. So what would we get? We'd get 1 times this, minus 1 times this, plus 0. Okay? Of course, there are many ways to get the determinant. I could do some row manipulation first that might make this even easier. But in any case, what do I have here? Well, I have 0 minus 1, so I have a minus 1 here, and I have minus 1 times 1 minus 0. So I have minus 1 times minus 1, that's minus 2. So that tells me that this matrix is an invertible matrix over the rationals. So this is invertible. Over the rationals. But think about what happens if we have this same matrix over Z2. Is this going to be invertible? And the answer is no, because minus 1 is the same as 1, and minus 1 is the same as 1. So this is the same as 1 minus 1, or 1 plus 1. 1 plus 1 is equal to 1 minus 1 is equal to minus 1 minus 1. These are all the same in the field with two elements because negative 1 is 1. So we have a determinant of 0, which tells us that this is not an invertible matrix. If we want to row reduce to try to see what happens, I can see that one of these rows is dependent on the others, or the same. I can see that the columns are dependent on the others. And how is that? Well, maybe let's look at them as columns. I don't really care which way I do it. We have a nice symmetry here. But if I add the first column to the second column, what do I get? Well, I have 1 and 1, which is 0. I have 1 and 0, which is 1. And I have 0 and 1. And lo and behold, I have the third column. So the sum of the first two columns is the third column. The sum of the first two rows is the third row. If I tried to row reduce this matrix, that means I could get a row of zeros at the bottom, and I would just have, let's see, the following, which is 1, 1, 0, 1, 0, 1, 0, 1, 1, and I row reduce using that. What we already know, I row reduce again, so what I'm going to do is I'm going to add row 1 to row 2, and that's going to give me 1. Well, I should have, let's switch them. Doesn't really matter. We're going to get there very quickly, no matter what we do. Okay, so now what I'm going to do is I'm going to add the first row to the second row. I still have a 1, 0, 1. I still have a 0, 0, 0. But what do I have here? I have a 0 and a 1 and a 1 and a 0, which is a 1. And that's it. That's the row-reduced form of our matrix. We have those two pivots right there. So things are very different. We're not going to get a row of zeros if we try to row reduce this over the rational numbers. As a matter of fact, maybe let's do that really quick as well. 1, 1, 0, 1, 0, 1, 0, 1, 1. And you know what? If I'm allowing, depending on what I want to do, I will switch the first two. Oh, sorry. I will switch the first two, the second two rows, and then I'll add the first to the second. Or no, I'll subtract the first from the second. So I have 1, and now I have a minus 1, which is not equal to 1. And then I'll subtract this row from this row. I get 1, 0, 1, 0, 1, minus 1. And I get 0, 0 because I'm subtracting. And then 1 minus minus 1 gives me a 2 there. Of course, then I can add half of this row to this, and I can subtract half of this row to this. And I get that, as you can see. If we wanted to, include, just multiply this row by 1/2, I could do that as well, or leave it depending on what my intention is in this row reduction. But in any case, you can see I don't get a row of zeros here. So yeah, don't think that just because the set of two elements is contained inside the rationals, don't think that F2, or the field with two elements, is a subfield of the rationals. I mean, it is as just pure sets. If we're just thinking about sets, then yes, that subset symbol is okay. But if I want to think about it as a field, no. So we'll see different things like that when we're working with these finite fields as well. But that's what I wanted to say there. If I were to row reduce this over the reals or the complex numbers, it would be the same because they do sit inside each other. So that would not happen. And there you go.